cooling curves and heating curves are used to track the amount of energy necessary in order to change the state and temperature of a substance as it goes from liquid, solid, and gas states. A cooling curve is set up the same way as a heating curve, except it will go downward in trajectory along the y-axis, which is temperature. And then along the x-axis is the value of constant rate heat added. Now, to use these cooling curves in order to find the amount of energy needed to change the state and the temperature of objects, you must create a curve that is flat when an object is not changing temperature but changing state, and has a downward temperature in cases of cooling curves when the temperature is decreasing and the state is not changing. Water, which is the example we were using today, has a heat of fusion of 334 joules per gram and a heat of vaporization of 2,230 joules per gram. Now, this is when a water substance is in the gas stage and the temperature is decreasing. But then once it starts becoming a liquid from a gas at 100 degrees Celsius, which is the boiling point of water, it becomes flat, and energy added is only changing state and not the temperature. After it has all completely become a liquid, it will start to decrease again in temperature until it reaches 0 degrees Celsius, which is the freezing point of water, in which case it will become flat again as the state changes. And after that, to make the solid any cooler, it will continue to decrease in temperature. And that is the basic outline of a cooling curve. Now, different parts of this must be calculated using different equations. Heat of vaporization and the heat of fusion are used stoichiometrically at these locations. At the other locations where delta T is changing, Q equals mc delta T, mass times specific heat times change in temperature, in order to find the amount of energy used to change a certain mass of substance a certain amount of temperature, and without using stoichiometry, like in the flat portions, where the value of delta H of vaporization or formation or fusion, is joules over gram, and can stoichiometrically using grams or mass of water be used to find the amount of heat added in order to change the state. An example problem is if we have 58.0 grams of liquid water and it is at 32.0 degrees Celsius. And then you want to change it so that it is completely frozen. Then you must find the amount of energy used. To start, you would create a graph, the cooling curve. Temperature on the y-axis, and heat on the x-axis. This curve starts at 32 degrees Celsius, and then will from there decrease as heat is added, as temperature changes, until it reaches 0 degrees Celsius, the freezing point of water, at which point it would level off and become flat. Now the goal is to calculate using Q equals mc delta T and the heat of fusion of water to calculate the amount of heat that must be added in order to achieve this. First part is the temperature change. And then the second would be heat of fusion, which would be solved using stoichiometry. Part 1, Q equals mc delta T. Mass is given in the correct units of grams, 58.0 grams. Specific heat of water is known to be 4.186 joules per gram degrees Celsius. And delta T is equal to negative 32 degrees Celsius. To have this plugged in now, Q is equal to 58.0 grams times 4.186 joules per grams degrees Celsius times negative 32 degrees Celsius. Just when you solve that out, Q is found to be negative 7,770 joules. Part 2, stoichiometry is used using the heat of fusion for water, which is 334 joules per gram. And we start with a stoichiometrical value of 58.0 grams of water times 1 gram of water per 334 joules, which gives us the value of a negative value of 19,400 joules. Now, to find the total heat change, we simply add parts 1 and 2 together to get our final answer for the amount of heat necessary to freeze water from a 32 degrees Celsius of temperature, which is negative 27,200 joules of energy.